Good evening. I was not following the survey closely. I was getting nervous for the talk. If I understand correctly, so 50% of the people in the room sort of would prefer not to have the second long talk. Is that right? Well, I'll try to make it short, and Petra will actually guard me. So this is much less technical than Jeremy's talk, and it's more about the previous 2 years and my own experience, how I ended up developing a simulation tool with two ladies, two programmers that I think are one of the best programmers I've ever met before. One of them is Petra, she's present here. Another one is Gabriela, she will be presented virtually in the talk as her avatar. So I'll mention her when her times come. And with a group of other researchers from the BISOP, that's the Center for Modeling and of Social and Biological Processes. Together with Petra, we're from Czech Academy of Sciences. So this is the outline of my talk. So I'll try in the first 2 minutes to tell the main message and then some of the details. There will actually be some Python code as well with appropriate alert, but not much. So what is this? This is actually an agent. A computer science talks about agents as sort of abstract entity, a piece of software encapsulated and situated in the environment. So the agents are reacting to the environment through the sensors, and they are acting upon producing actions and influencing the environment. So there's an interesting theory about agents that's part of a computer science, and one of the types of an agent we like is the agent with state. So an agent that has internal state. Some of you might be familiar with finite state machines. So this is something like you put a finite state machine into an environment like aquarium or something, right? But the important thing is that the agent remembers its state, and the state influences actions in the future. So in multi-agent systems, we are interested in what happens if you have a bunch of agents situated in the environment, interacting among each other and with the environment. And this is actually a sort of modern approach of modeling different phenomena. We have multi-agent models in physics where the agents can be particles. And the interesting thing, what the natural sciences and physics like to observe is that you have a simple model of the individuals, the agents, and some complex behavior emerges. Like we've seen the life. These are cellular automata, right? I mean, very simple rules about how to behave based on the neighborhood of as a cell. And we saw a slider running. We saw a slider gun producing the sliders. You can create logical functions out of that, right? It's Turing computable. It's like amazing. So biologists like that too. The agents can be like some animals in an ecological niche. So also in social sciences and economy, multi-agent systems or agent-based models are really popular, and we can actually use them for epidemiological modeling, where the agents are humans and they are interacting through their connections by social networks. These can be your personal contacts, this can be your friends on Facebook, and so on. So these connections can be of different types. A neighbor, lover, somebody you met on a bus, and so on and so on. So in epidemics modeling, we are studying how an infectious person can transmit the disease through the contacts, and then what's the degree of the epidemics. So yeah, that's basically what the talk is about, and now a couple of details. the epidemiological models. To be fair, the first epidemiological model is actually 100 years old, and it's been described by those differential equations. This is actually simple. You divide your, so think about some movies about zombie apocalypse, right? So you divide your population into 3 groups. The one is the infectious people, that's the capital I. The one is healthy people, but you know, these are medical doctors, right? So healthy doesn't mean anything. So they're susceptible, right? Waiting to be infected. And then you have recovered. That's the optimistic way how to interpret the R. It can be removed. That's more of a neutral term. So, and then you have rates how to shift from susceptible to infectious by getting the disease, right? So we have a perimeter beta, that's infection rate. It depends on your contacts with the possible infectious people and some objective measures of the infectiousness of the disease, right? And then you have a recovery rate that can be viewed like 1 over gamma means days of the infection, how long you're sick. And then you're basically saying, well, on each day, some part of people gets from susceptible to infectious based on the number of infectious people, the ratio, and divided by number of population. So there's nothing special about this, and actually we can program it in Python very easily. So this is the nerd alert, and now there's a Python code. It's really simple. You use SciPy and just remember the formulas. So you just create a Python function, put some of these parameters, and then just call the integration function from SciPy, right? And then you're getting these nice curves of infected people, recovered people, susceptible people. So you can see, I mean, that's pretty much an epidemiological model. Without good perimeters, the beta, the gamma, without considering how they are changing in time, this is pretty much the same as those like Excel tables with exponential functions that some of the experts used at the beginning of the pandemics. So yeah, makes sense, but there's a lot of research how to assess the exact values of those perimeters. Well, we have started our model basically by extending this SIR model into having more states, but we're still having an agent with states, right? So these are just detailed way how you go through the disease. So forget about this for now, and so you're susceptible. You can have false symptoms, but let's forget it. You're not getting directly into infectious state, but you have the so-called exposed state, where you're having the disease, but not actually having the symptoms and so on. With the symptoms, it's also interesting because you can have the COVID disease by being symptomatic or asymptomatic. So this is the asymptomatic way. It usually ends in the optimistic R, so you recovered. And then the symptomatic way, where you have some phase, couple days being asymptomatic, then symptomatic, and then either recovered or some fatal cases as well. And so this is just a finer states model. And the important thing is that these depend on the perimeters of the disease and maybe on your individual perimeters. Either you are healthy really, so you're not getting symptoms, your disease will last less days and so on. But this part, how to get from being healthy to being exposed, to get the disease, to get infected, it actually depends on the context, of your context. So just briefly, why do we have this mirror of those states that are the same as here, but with the D? These are detected states. And it reflects the sad truth that we're not, in reality, we don't know how many people is infected on a certain day, right? We only know how many people have been detected to be infected. And this might be 20%, 30%. So that's why we have those, and these arrows actually means testing and being proven to be infected. So we have some kind of observational layer of our simulation here. This is what we get as the numbers that were being published, still are, but nobody's really interested now. And this is the sort of objective way, like the objective numbers of infected people, exposed people, and so on. We don't know much about those. Okay, the state transitions in this agents with states are interesting because the transitions going from exposed to infectious and then to recovered are actually based on data from medical research. So we have those curves, and they are basically statistical distributions. And in our simulation, we just generate a random number for the individual based on this distribution. And you see these are not normal distributions, for example, right? And so there are approximations based on real data, but this allows us to have pretty detailed model for those state transitions. The only state transition we don't know much about, let me go back, is this one. How you actually get infected, right? Okay, so for this we need the network of contacts, and a good one. So we can study how contacts look like according to the age. This is a research by Prem and colleagues, and it shows age groups and intensity of the contacts between those age groups. So you see that's sort of interesting. You see you're basically meeting the people your approximate age. That's why we have the dark diagonal. Then you have parents with kids, grandparents with kids, those like darker areas. So this is sort of interesting but very static point of view on the context. Still useful. Then you can have different contexts in different environments. So for the epidemic modeling of respiratory disease, it is important to see if the contacts happen within a family, lots of contacts, school and work, quite a lot of contacts, visiting your friends, pubs and restaurants, not much of shopping and services. So this is the division of contacts according to the environment. And it's important because different environments are dangerous in different ways. If you're living with somebody, you have a high chance to get infected. If you meet somebody on a public bus, you're probably very unlikely to get the disease. A dynamic point of view, how these contacts change, is this. This is a calendar of contacts from the beginning of the epidemics till the end of the first year. And so from the research, you can actually see, this was the lockdown, right? We still remember. So the contacts drastically fell down. Then in summer, pretty much the same level as before the pandemics, then another wave, another lockdowns and personal limitations in contacts. So this is interesting, and for this we were actually using the PAQ research project that's Life During Pandemics, and they have each 2 weeks they have questionnaires for groups of people, and they gather the information about the contacts. So we know different, as we've seen here, we know different types of contacts, but we can also break it down according to the age of the people and so on. So this was invaluable source of dynamics of the contacts. You can also use something like Google Maps. application interface that we're also using for sort of reality check if the research actually makes sense. Another Python code, I guess. Yeah. So all this information about context of people can be expressed by the graph, right? For the prototype solution, we actually use a cool library called NetworkX that I would recommend to everybody who wants to work with graphs. That's pretty versatile, lots of graph algorithms. The graphs are cool. You can put anything into the nodes. So here we have an example. So you see we have a node called Romeo, we have a node called Juliet. We're adding an edge. We have a bunch of nodes about the Montag family. We have a bunch of nodes of Capulet family. So you see that we're creating a prototype model of Verona from the Shakespeare play. And it worked nicely. So this is the graph. You see Romeo here, and then this Montag family here. We have Juliet here and Capulets here. The play is actually beautiful. It has 36 characters, and we have everything. We have different families. We have the House of Prince of Verona. They have a super spreader event, the ball, you remember, right? Everybody who means something in Verona goes to the ball. That's heaven for COVID. Right? And we have different types of edges, families, and like work, and so on and so on. So this was our prototype model. It worked very well. Unfortunately, when we moved to something bigger, like the model of a Czech county, which we call the M-town, because at the beginning we didn't want to tell the truth that it's Hodonín. Because we wanted to test it on agents, but you know, it can get personal, right? Our colleague Josef Schlerka from the institute actually says that epidemics is one of the phenomena that we cannot test on people. I think he even said unfortunately. So, but actually the different different policies, how different countries actually dealt with the pandemics were sort of some you know, tests on people and experiments of people. So now we have lots of interesting data. Nevertheless, we're testing on agents, but we need to create a simulated Czech county. We decided for Hodonín because it's relatively isolated and a good size. Now, all those jokes are about Bruntal, right, in Czech, so Hodonín is fine. It's, so we have something like half of the people living in the city of Hodonín, half of the people living in neighboring villages. It's sort of a, what they call it, a travel to work area, so we don't have that many exports and imports. That's why we haven't choose, for example, what, Blansko. Because everybody goes to Brno every day from Blansko. This 60,000 people resulted in 2.5 million of edges of those contacts, and they were divided into 30 layers representing families, school, workshops, cafe, restaurants, public transport, and so on. Yeah, we already understand that. And this actually showed that we have, and this is Gabriela, we were looking for somebody who is the similar age as Gabriela. Gabriela was finishing her master's degree at the beginning of the pandemics. So out of the simulated population, we were looking for a lady, a student, age 19, and we found one in Hodonín. So her name was 29,691, and the nickname is Gabriela. It actually has an address, so these are like GPS coordinates. It's not the real Gabriela, but it's a real address in Hodonín. She has more than 200 contacts, like young people are socially active, they have lots of contacts in schools and so on and so on. And we can actually study what happens in Gabriela during the pandemics. So this is why agent models are good. We have sort of a microscope. We can take, how's Gabriela doing? Oh, she's not alive in this world, so let's run the simulation again, right? Gabriela's doing good. Unfortunately, the network X that I recommended before does not scale well. So for the size of Verona, having dozens or hundreds of people and some hundreds or thousands of edges is fine. But what we needed were more than 2 million edges. And all of a sudden, we had to re-engineer, and that's a heroic work of Petra, that we actually need to use sparse matrices for the edge representation. That sort of makes sense, right? A sparse matrix. Because for 60,000 people, you actually have something like, 3 billion of possible edges. That's a lot of edges, but we have only 3 million there, so we have 1/1000th of edges. So we represent the edges by sparse matrix. That's a CSR matrix from SciPy, I think, and then lots of NumPy vectors. And the only point of doing this was really to make it fast enough. So it boils down to have the edges represented by a bunch of arrays, vectors, that we can filter by Boolean masks. So getting all the contacts of one person is not that nice as before in Networks X. So you have to filter, use Boolean filter and the fancy indexing slices of the vectors, and then doing dot products and stuff like that. But we ended up to make it fast, I don't know, 100 times faster than with Network X, maybe even more. So now we can run the simulation in Hodonín, where like 1 year of pandemics takes minutes to half an hour, depending on the complexity of the policies. So this is how the code looks like. We have this simulation engine, that's why I say highly optimized, because it's using NumPy, and for me it's sort of a magic. Runs on cluster. We typically have to run 100 simulations of one scenario to get some statistical results. And then we have the data from the points of interest, like schools, shops, workplaces. So we're collecting these data to actually create the graph, and some daily epidemic data and weekly social data from the life during pandemics. Of course, we need to have some expert estimates for the parameters. We have to rely on those. They were changing during pandemics. That's sort of interesting, because we had different mutations, but also, you know, the research at the beginning, we didn't know anything. So the research reports were improving on those parameters. Nevertheless, we found out that we still need some kind of parameter fitting. That's like hyperparameters fitting in machine learning. So that's pretty much the same here. So we're using methods from grid search to optimized evolutionary strategies, the covariance matrix adaptation evolutionary strategies, that's sort of highly optimized for finding a good hyperparameter fitting. So that's how the code looks like. And now to get you a flavor of the simulating scenarios. So this is one of the interesting things that was during the fall 2020, where we were simulating what what does it mean to do contact restrictions. So without a contact restrictions, you see that the pandemics in Hodonín, well, all those results are for Hodonín, right? So the pandemics in Hodonín gets pretty big. And you can also see that we show two graphs. These are all infected numbers. So this should be the objective number of infected people. So at one day we have 6,000 infected people. So it's pretty much, you know, where like all the Hodonín gets it during this 1 year. And this is the detected infected. So these are the numbers you can see in the news, right? So when we're fitting the model, adjusting a bit of those parameters, we actually have to deal with those detected numbers. And these we are getting as sort of the result of a simulation. They can be right, hopefully, right? So that's the problem, that the objective data is this, right? Another interesting scenario which we can do, because we have the layers of the context, so we can say if there is a contact tracing procedure, if you're infected, you have an interview with the people from the hygienic service, and they ask you how many people you met last week, right? And so people, at the beginning, people were sort of honest, but still they don't remember everything, right? So we can actually say that we have categories of contacts like family, and you probably remember who your wife is. So if they ask you if you met your wife in the last week, you probably be honest and tell them. Work and school, usually as well, right? Leisure and some other stuff like public transportation, pubs, probably not. So these categories can have different rate of how many contacts you actually tell them that happened. So we can think of different contact tracing efficiencies, like this vector for these four categories. 111 means ideal. You report everybody. Well, it never happens unless you have a smartphone with some app that reports instead of you. And then you can be sort of reporting family only, for example, right? You don't want to report your colleagues from the work and so on and so on. So we were testing again, efficiency, how we can beat the epidemic wave depending on this contact tracing strategy. So you see no tracing, big epidemic, ideal tracing, small epidemic. But the interesting thing is that if actually people report family, school, and leisure, for example, having some kind of, I don't know, record tracking in restaurants, then we're pretty much the same as the ideal tracing. So that's sort of interesting. Family only, sort of middle type of epidemics. Back to Gabriela. This is actually interesting. I told you that we can take a sort of a microscopic level and observe what happens to Gabriela. So we were doing the party scenario, the sort of super spreading events, and these are like three different scenarios. And so it's interesting that in one scenario she is exposed. She's actually getting infected, but no symptoms. So after a couple days, she doesn't even know she has it in this scenario, right? But she was infectious. Another scenario where she has symptoms. She was detected by quarantine, so somebody reported her as a contact because it was a big super spreader event. So she gets reported and go home, right? So the quarantine was actually nicknamed Eva by another important member of our team who was responsible for starting the efficient quarantine procedure the first month of the pandemics. So Eva was sort of a strict lady, good quarantine, actually. So, I mean, this was just to show you how this can be used as a simulation tool. And in the last part, I would like to show you that you can actually use the same approach, change the graph, and get also interesting results. So we still have the multi-agent system model simulation engine, but instead of using Hodonín graph, we now have a different graph of context. And this is a research we did for the Ministry of Education, because they were interested about the efficiency of different measures in the school environment. So they actually took one school in Prague, which is represented here, and we had all the data about the school. So we had the like number of students in classes, you know, the schedules, the teachers attending, but also the students and teachers filled out a questionnaire about their other contexts, like who are their friends, with whom they share an office, and so on and so on. So what we got is a graph where we have 650 nodes, the students and teachers, and we have more layers, but the graph is much smaller, right? So the layers correspond to different classes and contexts in the class, out of the class, contexts in corridors, gyms, cafeteria, offices of the teachers, and so on. Again, different environments have different level of danger. And we use the same simulation engine. So here you see the graph for the teachers. Here you can see the graph for the students, so you can see the clusters represented by the classes, right? And the goal for this was first, I mean, can the Hodonín engine run the school environment and provide some interesting results? And we were surprised it can. And the government was interested in measures concerning the partial closures. Like, for example, if they close half of the classes, but allow the young kids to actually go to the school because it's most important for them. About weekly alternations, if we do weekly alternations, yeah, that's sort of understandable. And various testing policies. You remember the kids were tested, the teachers were tested. So do we need good tests, or is it okay to have some low quality tests? How often they should be tested, and so on. And this actually showed the relative efficiency of different measures. So first, static point of view, and this is in Czech, I apologize. We see the number of infected people that is broken down according to the environments. So this is in the class. No wonder, right? These people stay a lot of time in the class. Out of the class, nothing special. Teacher, that's this, not that much. Teacher-pupil, more. Some amount of those activities, afternoon activities, hobbies, and so on. Lots of for the lunch. So this is a static point of view from the simulation, cases in the environments. But we can also do comparisons of different testing and rotations, alternations of the in the school. So what we have here is this is basically closed school, and then this is basically open school, and in between we have different strategies like tests on Mondays and Thursdays with shitty tests, tests on Mondays and Thursdays with good tests, and so on. And this is tests and weekly alternations. So you can see that basically if you combine weekly alternations, even with bad tests, you're getting very low levels of epidemics in the school environment. So the testing, however annoying this might have been for the people, it was very efficient. Because you're doing it often, right? And if you combine it with the weekly alternations, it lowers the level of pandemics a lot. Of course, this does not tell you about the other problems that the students have with the weekly alternations or teachers, but it just can tell you the relative importance of the measures. So results like that you can get from the simulation, and you're using the same engine but different graph. That's sort of interesting. Actually, to conclude, we have created this model. It's on a GitHub, so you can see it on Epicity. We have different versions of it, and we're trying to make it from the specialized model dependent on a particular graph into more general tool. So now in Epicity we have the Hodonín data, we have the school data I just presented, and we have a couple, like 2 or 3 more graphs, one representing, what is it, Louny or something? Louny, yeah. We have a colleague who lives in Louny, so from some personal reasons we created a model of Louny region as well. Basically everybody can create, if you have some favorite village, or you can create a graph and play with the epidemics there. You can even name the nodes, like Gabriela or Mr. Novak, the unpleasant guy with the dog, and see what happens to him during the pandemics. So it's on GitHub Epicity. One thing these models are not very useful for is the sort of global pandemic situation reports and predictions. So for this is too microscopic, It's really good in showing the efficiency of different scenarios and sort of relative comparison. Is it better to close the bars? Is it better to close the schools? This model answers clearly for this. Right. Okay, so the final nerd alert. This is a group teamwork. So this is really a effort of different people from my colleagues Petra and Gabriela from the Computer Science Institute, to medical doctors like Jan Trnka, mathematicians like René Levinsky, Martin Schmid, and Vít Tuček, and programmers, sociologists like Tomáš Diviák, epidemiologists like Luděk Berec. There's lots of nerds involved in this for the last 2 years. Thank you for your attention.
Thank you, Roman. And we have some questions on Slido. So the first one is, according to your model, how efficient or bad the COVID restrictions were in Czechia?
Yeah. Well, it's recorded, right? No. Of course, the first lockdown was really severe, right? We didn't know what to expect, and you saw the restriction in the context. The contexts were low. You remember it. We were visiting maybe our grandparents, but maybe not even that, right? The life stopped. So this was, I think, an understandable reaction to the situation. But then in the fall and then in spring, the reactions were too slow, basically. So I think that the problem of the Czech Republic version of politics for the pandemics was that it was not in time. Then it resulted in the situation being bad for much longer. So the politics where you react on the number of people in the hospitals is really bad, because people in a hospital gets after 2 weeks of getting infected. So if you actually follow the daily numbers of infected people, you have 2-week advance, right? So yeah, of course a lockdown is efficient, but it should come in time, in a proper time. And if it comes earlier, then it can last for, I don't know, weeks and not months.
Thank you. Another related question is about how does it feel to know the truth and see the decision makers not respecting it?
Well, it has two parts. So the truth, it's very relative, right? The models at the beginning were really bad, and they were improving and improving. We didn't know much. The parameters of the disease were not right. You know, we had some forecasts that were not exactly truth. That it helps that we were different people, you know, with using different methods, and so everything went through the check of all those people. So we were not in a position of some other researchers that were presenting their catastrophic scenarios. Still, we were presenting some catastrophic scenarios, and we were right. Yeah, sometimes it's frustrating. Yeah. I hate going to the TV and being, you know, the sad guy in black and telling the bad numbers. So I'm glad I'm not doing it anymore.
Thank you. Another question is this or another COVID pandemic model robust enough for predictions and thus usable for restriction policies decisions?
No. Not, yes. It's not good for predictions. For predictions, the models that are better for predictions are based on the traditional equation-based models, but with a very fine and sophisticated setting of the hyperparameters. On the other hand, this model is pretty robust. So we run it, every experiment we run 100 times or 1,000 times, and we do sensitivity analysis and so on. So the results are not just one random experiment, but they are statistically sound. And they are good for assessing the efficiency of different measures. So relatively, as I've said before, you can tell, is it better to close the schools or the bars or the shops? We can answer this pretty certain. For forecasts, not really. Well, maybe for forecasts in Hodonín, exactly, you know.
Thank you. Another question is more technical. It's about NetworkX. So, do you know why NetworkX doesn't use sparse matrices directly? And could you perhaps contribute that feature to NetworkX?
I don't know why, but their focus is on being very user-friendly and general. So it's more like dictionaries, you know, and any kind of data you can glue to the nodes, you can glue to the edges. Well, I can actually imagine this can be done by using sparse matrices as well. But, well, I love NetworkX. When I first saw it, I was like, wow, this is a beautiful piece of Python code, you know. It's almost like mathematical. You write your code and it looks like the definitions. What's the neighborhood of a node, you know, and so on. So it's beautiful. Maybe it can be done to use the sparse matrices and scale better. But the generality of the approach and the interface is beautiful.
Thank you. Another question is about modeling the actual number of people who died. Have you tried that? When comparing data of deaths with previous years, which is much worse than reported?
Yeah. When we match the data, the daily data during the simulation, we use whatever we can. So we use the detected infected, we use the dead people as well. So that's part of matching the data, the model to the data. Yeah. So we're using that. Yeah. But we don't have any global theories about that. But in order for the model to, so we can tell the model performs good, the number of deceased people is actually one of the important sort of objective numbers. Unfortunately, the detected people, they seem to be very objective, but it really depends on testing policies, right? So for example, if you were forced to do the tests to go to the office, for example, you have a nice sort of uniform sampling of the population. So the data about the infections at that time are pretty good. But if you can avoid testing, so lots of people don't go there because they don't have to, and all of a sudden you don't have an unbiased estimation of the data. So testing policies are one important factor that makes the data more noisy.
Thank you. Sorry guys, there are plenty of questions in the queue, but we have to choose the last one because the time is running out. So the last one is, I didn't see a reinfection edge in the state graph. Can it support also that?
Reinfection. Oh, yeah. We were not considering this in this case, but it's actually, not difficult to have it in the model, because when you end up, I just show it. There's lots of nerd alerts, I apologize. So when you end up being recovered, you have some kind of rate going back here. So that's sort of easy. And we actually did a specialized research about reinfections. And this is interesting. We have 2 papers. One is being published, I think, and another is under review now. And so we have data about reinfected people based on, was it like reinfection of which type, or is it post-vaccination? So we have a nice model that using this engine for this special question, like what are your chances to getting infected after the vaccination, first dose, second dose, the booster, or after a reinfection, after infection, previous infection as well. So there's different risks, and so it's an interesting piece of research. We did something in that. I was just not presenting it.
Okay, thank you a lot, man. So one more applause for